Hello everybody, welcome back. You've probably noticed this chapter that we have been learning about rotational values and rotational dynamics and statics and that kind of thing, but also comparing them to their linear counterparts, their linear analogs, where let's see, force is analogous to torque, all right, and so forth. And we talked about how momentum, angular momentum, is analogous to linear momentum by way of the radius of a rotating object. Now we're going to be determining, or at least deriving, the equations for work and power as they pertain to rotating systems. All right, so let's go back and just start at what our equation was for work. We talked about it in a linear sense. Work, in its most basic form, we described it as force times distance. All right, now that distance could be a delta x, it could be a delta y. Doesn't really matter. I'm just using d, the generic d, for just a generic distance. Okay. Well, let's take these. Work is the equation that we want, and we want to take these and turn our force and our distance into their rotational counterparts. Well, you probably recall that force times radius equals torque, right? So therefore, force has to equal torque. I put an arrow over my torque. There we go. Torque divided by the radius. So let's put that in for our force, right? So work equals torque divided by radius times distance. All right. Well, we have a relationship between rotational distance, or I should say rotational, or angular displacement, and linear distance. And we said it was this, that our change in angular displacement was its linear counterpart divided by r. All right, whether this is delta x or delta y, it doesn't matter, but it's related by being divided by r. So that means then that our distance, our linear distance, would be r times change in theta. All right, r times your angular displacement. Let's take that and substitute that in for our d right there. So then we have our work. My w's are coming out funny. Our work is going to be equal to torque divided by radius times delta theta. All right, now you see what's going to happen right here. That radius is going to cancel out, and that is how we have our equation for rotational work. That work is simply torque times our change in theta. And you probably recall that, again, these are analogs of their linear counterparts. Torque is the rotational counterpart to force, and delta theta is the rotational counterpart to d right there. So we've got work. We also have power as well. All right. Power, our definition of power in linear terms was work divided by the change in time. All right, well, what if we put in our equation for rotational work, being torque times delta theta? Sorry, so torque times delta theta divided by time. All right, I kind of put time over here underneath the delta theta so you can see that. All right, well, what's delta theta over time? What is our angular displacement over time? That's angular velocity, right? So our power in rotational terms is going to be torque times angular, so it keeps saying angular velocity. It's really angular speed, all right? But it's our omega right there. And again, you probably remember this from our previous power chapter. We said that power was equal to force times velocity, all right? Well, then that means that, you know what, I accidentally put an arrow over the P right there. Sorry, and that means that force being analogous to torque and velocity being analogous to angular speed is going to make that statement still true. So this right here, torque times velocity, is what we've got there. Very much like our work equaling torque times our angular displacement over on the left-hand side. All right, so those are our two equations for rotational work and rotational power. Let's see. I'm going to stop at the end of this I'm going to stop right now, basically, and just pick up on the next example. The next 16 is going to be on, it looks like, making homemade ice cream. So we'll pick that up on the next video. So thanks for following along. I'll see you on that one.